Okay, testing. Can you guys in the Zoom hear me? Great, thanks Beatrice and Zichuan. Welcome guys, so it's about time to start, 5 p.m. So we're doing Math7502, this is our second session. This week we're doing a little bit more Julia, but we're also doing linear algebra. So if I can, I'll see if I can find a way to write, but it'll take me a moment to set this up. So bear with me. Okay, so I'll start by screen sharing. And then I'll want to open up the chat so I can see what you're saying. Okay, can you now see my screen in the Zoom session? Okay, for you guys hanging out at home, I'm just setting up the system in the room as well. Project onto the screen because we have a room full of about, looks like 20 people, I might guess. Okay, gentlemen over there, could you please space yourselves out a little bit? I need to make sure that you're going to stay healthy. Okay, great. Okay, now I'm just going to open up the files that I've got here. So the first thing I'll open up is Anaconda, which I've now put on my pin to the taskbar, I think this is called, which is handy. As you know, it takes a little while. Okay, Jupyter launch. Now I've saved the tutorial file that Yoni's provided for us. So if you go to Blackboard and you go down to the bottom of the course website that's attached to Blackboard, where you see the GitHub link. So you select the GitHub link and then you select weeks and open that. And you'll want to be able to download that, right? But this time, something seems to have gone wrong with downloading that file that Yoni provided, because there's no download button on that, on the GitHub website for the second Prax tutorial sheet. Okay, but that's not such a problem if you know what to do. So you have to right-click on that when you're there on GitHub, and right-click the raw button. Okay, there's a button that says raw in GitHub, R-A-W. You right-click that, and then you save as. If I remember right, that's how that worked, and then you can save it on your desktop or your documents folder and then open it just like I'm about to. Okay, so that's what I'll do now. Documents, and then tutorial2.ipynb. Okay. Great. And then I'll minimize Anaconda. Okay, now the second thing I want to open up, well, I'll just keep it in the background. I've got a PDF file. Now, basically, well, I'm not great at using Julia, basically, because I don't know all of the syntax perfectly. All right, so in order to understand what I'm seeing, what I usually do is I'll type up some code in Mathematica. Now that was part of the 7501 course that some of you did. Okay, so for some of you that might be familiar, but what I have is some comments, because I've commented what's going on in each of the problems. So I'll possibly need to refer to that from time to time. Okay, but that's here. And so I'll make it a little bit smaller so I can swap between these easily. Okay, so are we all ready? Let me have a look at the chat. I've accidentally minimized. Well, I want to get that back, so just a second. Yep, I'll go up here, chat. Okay, great. That pulls the chat back up. This is such a small laptop, so I might struggle a little bit with all of the windows that I need to keep open. Okay, anyhow, so I was hopeful that I'd be able to use the document camera together with this laptop and have it recorded on Zoom, but I think one day I just need to go in and practice that, because it seems to me at this point a little bit tricky, and secondly, it's somewhat far away from the PowerPoint. So right now I'm just going to assume that I'm going to have trouble with that, which would create a lot of dead air for you guys, which would not be good. So I'll do my best going back and forth between this PDF file and the Jupyter notebook. Okay, so our first problem would ask us to construct a 3x3 matrix A, then to take the trace, the determinant, and the inverse. Okay, so if you don't know what the trace of a matrix is, it's simply the sum of the diagonal elements. Okay, all right, so now how would you do that in Mathematica? Well, I would write this, the 3x3 matrix, something like this. Okay, so we'll take this matrix as an example. So you can see that the syntax is different and that it has curly brackets. But what you want to know is how to do that in Julia. Okay, so below that, I've got the code for Julia, how you input the very same 3x3 matrix in Julia. And now we put a square bracket to start with, and then we space out our entries using the space bar. And when we want a new row, we put a semicolon in to indicate that we want a new row. Okay, so let's go over here to the Jupyter notebook. Okay, Waals is saying I'm going to provide the file after finished. Okay, sure, Waals, I'll do that. Okay, so let me just ask you, do you want the real thing or do you want the PDF? We'll see, we'll see. Okay, anyway, so in Mathematica, you can save as PDF, so that's what I've done. You don't have to have Mathematica installed on your system in order to open a PDF, which is handy, right? Okay, anyway, back to this. So the first thing we need is to write using linear algebra, okay? And then Shift Enter to make sure that that will work for us. Okay, and it usually takes a little bit of time for these preliminary things to be loaded. Okay, so if that's gone through, then I'll just press Shift Enter in the second cell to input this matrix. Okay, so we see the asterisk was there for a moment, and now that's gone into memory. Okay, so you can see that that works. Now you want to try this out yourself on your own system and see that you can do this. All right, next, the trace. So as I said earlier, the trace is simply the sum of the diagonal elements of the matrix. So we can see that that would be 1 plus 1 plus 1. Okay, which we know is 3. So let's try this. Trace of A is 3. And let's just notice the syntax here. That's a lowercase tr and a round bracket. And we just put the A in because that's in memory above. And we've got the trace. Okay, the next thing that we want to do is calculate the determinant. So det of A. Now, sometimes it's handy to do this sort of thing by hand as well, so that you can see that your computer calculations agree with what you've got by hand. All right, so here we get 104 for the determinant of the matrix, and that looks plausible. Okay, so the next thing we're going to consider is a formula for calculating the determinant of a 3x3 matrix, and you probably would have learned this early on in your mathematical studies, like maybe a first-year university, or for some of you, high school. And so what that looks like is you would calculate the determinant of a 3x3 matrix by taking the element in the top left corner. In other words, the first row and the first column. Okay, so what we're talking about now is how do you do indexing, and how do I use indexing to calculate the determinant of a matrix? So that's the next part of this exercise, because indexing in any kind of computer software, well, let's say specific to mathematics or just computer science, indexing is a fairly important thing to be able to do. You want to be able to pull out specific elements of an array or a list or a string or something like that. Okay, so here the A subscript 1, element, first row, first column, is A square bracket 1, 1. Now, if I were to do this in Mathematica, I would put A and then 2 square brackets and then 1, 1, and then I'd end with 2 square brackets. Okay, so that's the A11 entry. And then remember, if you're using the formula to calculate the determinant, that involves some minors, which are determinants of some elements or smaller matrices, 2x2 matrices within the larger one. Now, if I just take the mouse, because I know that all of you should be able to see my mouse cursor. Is that right, Walla? Can you see my mouse cursor on Zoom? Yeah, good. Okay, so I'll highlight this. It's this one times the determinant of this section where you ignore the 7 there. I'm trying to highlight the 1681, right? So the determinant of that 2x2 matrix times 1 would be an important part of this calculation. All right, so the question is, how do I do that? All right, so we need a determinant of a 2x2 matrix. All right, so that we have below det A, and then what we have here is 2 colon 3. All right, now what that should be taking, if I remember right, is the second to the third rows of the matrix A, and then the comma tells us that we're taking the second to the third column within that. Okay, so that does give us this 2x2 matrix containing 1681, but we're applying the determinant to it. And remember, this is a scalar multiplication here, so we have just a star there. Okay, the next part is we subtract what is in the first row and the second column. So that's -2, right? And so A12, and then we're multiplying by another determinant. Okay, so this one is slightly different. So you'll see inside there, we've got A square bracket 2 colon 3. So that's this second to the third rows. But then we see something new here, square bracket 1, 3. So Julia has this nice way of saying I select the first and the third column out of the second and the third rows. Okay, now I did this in Mathematica, but it wasn't as easy to enter, let's just say that. Okay, so Julia's got some nice features in the syntax that are a little bit simpler in some ways, but every software's got pros and cons, right? So later we'll see how symbolic calculation is handy, whereas Julia doesn't do symbolic calculations. Okay, but a lot of the syntax is quite nice. All right, now continuing on, we then multiply by the A subscript 1, 3 entry, so top row, third column, and then multiply by the determinant that we get by crossing out the row and the column that that entry is in. In other words, So if I'm crossing out the 1, 2, 3 and crossing out the column that contains 3, 6, 1, then I'm left with 4, 1, 7, 8. And that's the determinant that I want in that formula, okay? Fortunately, that's fairly simple here in Julia because we just have det a square bracket 2 colon 3 for the second and third rows. And then we want the first and second column within that. And that gives us the matrix 4, 1, 7, 8. Okay, now let me have a peek at the chat to see if I've missed any questions. It looks silent, so I'll take that to mean that I'm going too slow. Okay, so I'll try to accelerate now. Okay, so let me have a look at the next part of the exercise here because I've written that in my PDF. Okay, so now we are up to, yeah, and you can see I had a little bit of trouble in Mathematica reproducing that, but maybe I'm just ignorant of some better code for that, okay? That's possible. All right, so scrolling on. So we calculated the determinant in 2 ways. Now, some of you may know that you can also calculate that using the entries in the first column. You apply a similar procedure to calculate the determinant, okay? So I think I'm going to skip that calculation. All right, now inverse. All right, so what you can see now is that I've got a symbolic calculation of the inverse of the matrix A. Now that should be the same inverse, all right? But what you see are rational numbers, represented as rational numbers in that inverse. And we can see that some of those have a denominator of 104, whereas that would have been simplified in other entries. Okay, so that's what Mathematica does. Now, in Julia, I understand, since it's not doing anything symbolic, it will want to take entries that are decimal numbers and then form an inverse from those decimal numbers. Now, those decimal numbers are approximations of well, they would be just treated as rational numbers, right? Because they're real numbers that have been truncated in the calculation of the entries of that in Julia. And so when you take an inverse, you don't get precisely the exact inverse. You get a close approximation because it's done with truncated numbers. So what we have here in the display for Mathematica is the recipe for those numbers, right? Whereas a decimal approximation is just an approximation of these numbers, for example. Okay, so let's have a look at our problem. What we wanted to do was take the inverse of the matrix A and then I think multiply the inverse by the original matrix and see how that was. Okay, so I've done that in Mathematica in 2 ways, numerically and precisely. So let's have a look at this in Julia now. So we'll enter AI. So AI is just what we're going to call the inverse, okay? So we're putting this in memory. And that's running, takes a little bit of time. Okay, so, and now we'll go and take the inverse of the inverse. And you can see that what we now have, even though we input integers, we can see that these are integers. They just have 0.0 after them. So they're floating point numbers in here, but you can see it's accurate, okay? All right, so moving on. Okay, so this one is somewhat of a theoretical exercise at first. So I'll just verbally talk you through that. Okay, so it says, consider this matrix equation. We've got a matrix C times a vector X, or a column matrix X. And then we add the transpose of X transpose D, and that's equal to X plus B, where those C, D, and B are given having 2 rows. Okay, and now what we're aiming to do is solve this equation for X. Okay, but we'll want to do a little bit of a theoretical calculation first, so that we can enter this in the computer more easily. Okay, so the first thing you can notice is that the transpose of the product AB is B transpose A transpose. So we can apply that to this first. So if we transpose X transpose times D, then what we have is D transpose times X. Okay, so that's our first step. And then next, since we want to solve for X, we would like to take X to the same side of the equation and collect if possible. So we'll then subtract X from both sides. But notice that X is I times X, as in the identity matrix times X. And that's great because that gives us an opportunity to factorize out the X and place it on the right of all of that, because now it's common on the right-hand side of each of those three terms. So we can factor that out and put it on the right-hand side, and inside the bracket on the left, we have C minus D transpose minus the identity matrix, and we're solving this equals B times X equals B. Okay, so that's great. So that suggests to us all we have to put in memory in Julia is, well, we might want to call A, as we have here, C plus D transpose minus I. Okay, so let's try this. Error D not defined. Okay, that's because I skipped this, so I'll have to go up here and include that calculation. So that should be in memory now, and now we'll scroll down and run this, and we'll put A in memory as C plus D transpose. Again, you've probably seen this before, but the dash, that's meaning transpose. Okay, that's Julia's syntax for transposing a matrix. Okay, great. And we see that we in fact have a 2x2 matrix A that's been returned. And so that tells you that somehow Julia knows what I is, right? Even though it could be a 3x3 matrix, for example, right? So it seems to have taken that from context, but I'm only guessing because we're adding two other 2x2 matrices. So that's rather clever. Okay, but it probably relies on having used this linear algebra package that we set up at the start. Okay, next we want to solve for X. Now, this is a lot like the syntax in MATLAB for solving a linear system, right? Whereas in Mathematica, to do the very same thing, I would write linear solve. Okay, so this is a bit more like MATLAB, the syntax. So X solution, A backslash B. Okay, so let's try that out. And it returns a solution, so great. Okay, let me have a peek at the chat. All good there, everyone at home in Zoom or wherever you are, maybe in the library? Are you still with me in the chat? I better check that. Just give me a thumbs up or a yes. Okay, great, good. That just tells me that I don't have to worry about it having been cut off. So great, thanks guys. I can see you're still there. Okay, great. So next there's some calculations on checking this. So let's just try this. Checking. So this is, I believe, the top expression up here that we're just going to run. Okay, 1.25, 2.3125, great. And now does that match the right-hand side? Yes, excellent, it matches. Okay, great. Now, I'm going to have to peek at my notes here because just staring at what says in 30, I don't immediately know what we're meant to do. So let's have a look. Okay, so after calculating that stuff, scroll down. You can hear my mouse now. I've brought in a mouse because I'm using this laptop, and I absolutely despise using the mouse on a laptop. It just drives me nuts. So I've got my own mouse here, so I should be able to operate this better. Okay, so the next problem. Okay, I think that's at the top of this page. Okay, so it says build a 5x1 matrix U of ones. Okay, and I've got the code here in Mathematica to do that, which would be constant array, and I would place the 1 in there, and I would tell the dimensions. Okay, the next thing we would want to do is build a 5 by 1 matrix V consisting of integers 1 to 5. Okay, so the numbers 1 through 5 is the matrix V. All right, and then what I want to do is take their dot product in two different ways. So remember that the dot product of two vectors is defined to be just multiplying their rows together and adding the result. So it's a sum of the product of all the rows together, all right? But the key is that you can do this conveniently with a matrix product if you just first transpose the one on the left and multiply them as matrices. And that gives you the same thing, the dot product. So in Mathematica, I've got to get rid of some extra brackets because when I do it with matrices, I get some extra brackets when I was hoping to get a scalar number. So I've got to get rid of those. So I think in Julia, that's unnecessary. So let's have a look. Okay, so the first one is fill. We've got a round bracket 1, 5. So this is giving us a vector with 5 entries, but all of the entries are equal to 1. Okay, now the next is what would be table in Mathematica. So that's just 1 : 5. And that gives me 1, 2, 3, 4, 5 in a vector. Okay, and then here you can see that we have the calculation of the dot product in two ways. So on the left, just dot u comma v, and on the right, u transpose times v. And now I see that the asterisk takes care of matrix multiplication, whereas in, say, MATLAB or Mathematica, you would need to use different syntax and different in each one, okay? Okay, now a second thing I want to note is that we don't need to put a round bracket on either side of this. So just putting the one thing, comma, the next thing, and then calculating that, that gives us this 2 tuple below. All right, so let's try that, and we do get 15, 15. Okay, so 1 + 2 + 3 + 4 + 5. That's a triangle number, and that adds up to 15. Okay, any questions, anyone? All right, so I think I'm getting better at multitasking at this point. So if there are any questions in the audience too, you want me to address or Walla to address, just please get one of our attention and ask your question. Or if you have any questions in the chat, go ahead and ask them too. All right, I think I need to accelerate a little bit. So let's have a look at the next one. A equals reshape, collect. All right, so we want to know what this is asking us to do, because if you're not familiar with Julia, you just see these commands and you wonder, hey, what's the question? So let's have a look at my PDF here. Okay, so my notes say that we make a list of the integers from 1 to 21. All right, now the prime factorization of 21 is 3 times 7. So then we should be able to form out of that a 3 by 7 matrix. Okay, so that's the next step. From that, form a 3 by 7 matrix in which we count from top to bottom. Okay, now that's exactly what I've got here displayed. All right, you see 1, 2, 3 goes top to bottom here. So that's what we're aiming to do in this. So that's what this command does. So on the inside, we've got 1 to 7, okay, and then this collect. I don't remember what that's doing because, yeah, I mean, I need to try that piece by piece to know precisely what that's doing. But once we form this list of integers from 1 to 21, we reshape it to be a 3 by 7 matrix. Okay, so maybe that syntax is somewhat confusing, but I guess it maybe depends on your perspective. Okay, so let's have a look and try that out. A equals reshape. Okay, so that gives us what we were aiming for. Now I'm going to try to get fancy, okay? So not always good at trying new things, but let's just do that. So up here, I remember I can go insert, cell above, insert cell above. So let's try this. Okay, great. Now I've got a new cell. So let's take a piece of this out because I had a question earlier. So if I just take this, collect 1 and 21, are we actually getting the numbers from 1 to 21 or are we getting something else? Okay, so that's running. All right, now I see that we have a column vector from 1 to 21. Okay, so that answers that question. And then the reshaping of it is what would be partition in Mathematica, so breaking this up into triples. Except here you've got a 3 and a 7, so anyway. Okay, so now I think we understand that, so let's move on. Now rank. So we're entering into memory. So have I done this? I think I have. So yeah, so I think I'm up to that. I've got the matrix A in memory. Now rank, this is the dimension of the row space of the matrix A. But there's a nice result that says that the dimension of the row space of a matrix is equal to the dimension of the column space of a matrix. And we call that the rank, okay? So in other words, you can use row reduction, Gauss-Jordan reduction, to calculate the row-reduced echelon form of the matrix. And then you can look at that to find out what is the dimension of the linear space consisting of the rows, or the row space. Okay, and I'll just skip ahead here and talk about this because putting in row-reduced echelon form, or RREF, into Julia, we get the row-reduced echelon form, and what we see is we have two pivots right here where this one has zeros below it, and then there's another pivot here. This one has zeros below it, zeros above it, and zeros to the left of it. So those are two pivots. So these two rows, the first two rows from top down, they span as vectors the row space of this matrix. But also, since the row space is equal to the column space, we know that the column space has dimension 2. And in fact, the column space, so I'm trying to highlight that, but that's not working. So the first two columns are vectors that span all of the columns of this matrix. So in other words, all of the other columns should be linear combinations of the other two columns, the leftmost two columns. And you can see that straight away. It's obvious, right? Because, for example, the vector consisting of entries -1, 2, 0, as in the third column here, that's a linear combination of the first two vectors, in first two column vectors there, because it would be -1 times the first one plus 2 times the second one. All right, and that's a linear combination. Likewise, you can obtain all of the other columns in that way. Okay, so below we're going to see exercises on how you actually find those numbers using Julia. But let's go up here and run this stuff. So rank, you can see it's going to be 1. So yes, that works, great. Okay, next we've got to put in using row echelon. I can see I get an error here straight away. Okay, so this is not enough here. So we need something else. So I'm going to go up here and insert a cell above there, and I'm going to have a peek at my cheat sheet over here, the PDF, because I did this at home, and this is the first time I'm actually running this Jupyter script here on this laptop, right? So I've used my own PC at home to try this out together with Mathematica so that I understand this. So let's have a look at what I meant to enter on the computer beforehand to get this package to work. Okay, so my notes tell me that I need to write import. So let's try to shift this over a little bit so I can see it. So import, IMPORT, and then uppercase PKG, semicolon, and I probably need a space, so I'll put one. Okay, uppercase PKG dot add, and then round brackets, and then what do I need to put inside? It's probably row echelon, but I'll have a look. Yep, row echelon with an uppercase E. And remind me if I don't spell that correctly. Okay, row echelon. Does that look right? No, it's red color, which kind of worries me, but let's try it out. Shift and enter, and I can see it's running now, which is a good sign. Taking a little while. Okay, great. Now, some of you were having some problems last week in loading some plots. So you might just take note of what I've put in here, right? Because sometimes being not totally familiar with all of the things that you have to load here in Julia, sometimes we've put using, and this time I've put import, right? So I don't know a lot about that. I've just done some trial and error here. Okay, so it seems to still be running. Okay, so we're gonna have to wait a little bit. And maybe in the meantime, I need to make some small talk or have a look at the chat or something. All right. I guess it would have been wise for me to do this earlier, but hey, I reckon that a lot of you are having the same issue and having to wait for your computers too. So this may not be the worst thing ever. But if this goes up on YouTube, and I think it will, well, dead air is not really great. Anyway, what can we do? Okay, so let's just have a chat about what we're doing next while we're waiting. Okay, so next, I mean, I talked about the column space, and for example, how would we work out using the computer that the third column was equal to -1 times the first column plus 2 times the second column. So that's what you see here. It's in 46 is saying. Okay, and I can see that that seems to be saying a whole lot of stuff, updating, but now it has a number 18 next to it. So I think that's good. So let's try this next. I'll try a row reduced echelon form here. Not defined. Any tips, Walla? Yeah, so I'm probably missing something, but I bet if I just look at my PDF, I would have, oh yeah, using row echelon. Okay, great. Thank you, Walla. All right, so I'll go up and insert another cell. So using row echelon. Okay, shift and enter. And that's running. Seems to have gone through. So now I'm tempted to go and make a new line and put row reduced echelon form, but I want to know a question. Is it going to care about the order? So I'll go up here and try it again. Okay, great. It doesn't care about the order. That's good to know. Yeah, great. So yeah, like Mathematica, whereas in some other languages, the order in which you entered things would be an issue. Okay, great. So that runs. Now, like I was saying earlier, what we're going to do is we're going to work out that the third column is a linear combination of the first two, and we're going to get those coefficients, but they're obviously -1 and 2, right? Now, so how we do that is we use indexing. So this is another chance for you to practice your skills at indexing, or at least remember what you're meant to do. Okay, so we have x3 equals uppercase A, left square bracket, colon, and then we have comma 1, colon 2. So what that is basically all of the entries. So in other words, every element of the rows as we go through columns 1 to 2. All right, now in Mathematica, I would put it an all there rather than the colon. All right, but this gives us precisely that. This gives us columns. Columns 1 to 2. Okay, and then here we have a backslash. So what we're doing is we're solving a matrix vector equation where you might imagine an invisible vector z, so that what we have is this, the left part, the first two columns times the vector z equals this third column, which is another vector, right? So we're solving that system. Okay, so let's try this. And great, that works, and it's precisely as expected. We get -1 and 2 in our vector z, but what that's giving us is the coefficients, right? What we would multiply together to realize that as a linear combination of the first two columns. Okay, now down below we've got a lot of the same, so I'll just skip that. But I have to stop somewhere where we're seeing something new. Okay, rank A, well, that's still going to be 2, I believe. All right, so let's go to this point. V equals -1s, 3. And you can see down below what the output is, so it's not hard to guess what the syntax is doing. It's just giving us a vector of the negatives of -1, but 3 rows of this. Okay, so let's run that, because that puts that into memory, and I'll have a peek at the chat. Okay, so yeah, I see Zichuan was very helpful earlier using PKG. Yeah, thanks. I sadly didn't see that comment earlier. Okay, but we got it. Okay, now norm. So the norm, if you just do this norm of V, that is the Euclidean norm. So this should be the square root of the sum of the squares. So in other words, the square root of 1 plus 2, sorry, 1 plus 1 plus 1. So the square root of 3 and 1.732. So this is one of the things that I thought would be a good idea to memorize when I was a kid. Okay, so that's the Euclidean norm, and you can see that this matches the square root of 3. Now, I want to ask another question because Julia should be great at reading LaTeX. So let's try this. I'll insert another cell above. Okay, and if I remember the syntax right, LaTeX would be \SQR. And let's go 3. Okay, and now tab, was it tab? Something like that. Space. Tab. I've forgotten now, but you should be able to change that to LaTeX, right? Or am I remembering this wrong? At least it worked for pi. Okay, but now tab. There we go. Okay, so it works for pi, but I don't seem to get any pretty symbolic something for the square root of 3. Okay, which I was hoping for, but that's good to know. All right, now next, norm V comma 1. So what is this? Well, this is the L1 norm, which is the sum of the absolute values of the entries. Okay, so we can see since we have -1, -1, -1, the sum of the absolute values would be 1 plus 1 plus 1, which is 3. Okay, so that's a different kind of norm, which is useful for some other things. Okay, now also we have the infinite norm. All right, so if you were writing this, you would write, you would put V, and then on either side you would put 2 vertical lines, right, on either side of the V. I wish I could show you here, but I fear that I'm not going to be able to get the doc cam to work with this. If we finish early, then I may have a go at that. But anyway. All right, so 2 vertical lines, and then you put the subscript infinity at the bottom right of that. Okay, but this is, and I'll just run it. This is the maximum absolute value of the entries. Okay, and we got 1. All right, so let's just try this again on the vector 1, 2, -8, 3. Okay, and we get 8 just as expected. All right, now normalize. So what we're doing here is we're forming a unit vector. So this is simply to divide by the norm of the vector, which produces a unit vector. But there's a nice command called normalize that does that for us. Okay, and there it is. And now let's check, because we've put this in the memory now. V is the normalized of the earlier V. And we'll just check that the norm of this is actually 1. Okay, and that looks good. All right, next we come up to seeing some fancy stuff. Okay, so I'm going to check my notes on this. And I think this is the one that I want to skip, because for starters, I don't think I quite got the plot running. I'll have a go at it. I'll press Shift-Enter and we'll just see. But I don't want to spend a lot of time talking about this problem, because I want to spend more time talking about the next one. And well, we've got 15 minutes to the end of the hour, and we're meant to really knock off at 10 minutes to the hour, so you can possibly rush off to another class. So if you need to rush off to another class at 10 to the hour, go for it. I'll just keep talking because this is all recorded. All right, now I kind of regret running that because it took a while. And yeah, I get an error, so I'm not going to fiddle with that now. Okay, but you do get a nice pretty picture about some random things. And so it would be nice if you can get that to work on your own. Okay, so next one. Now, I'm going to have a look at the Mathematica PDF that I've got over here, because it gives us some notes on this. Okay, but I've got to scroll over a little bit, scroll down. All right, and my notes on it start here. Now, so I'll draw your eye to the biggest thing here, right? So this matrix here, this is called a Vandermonde matrix. So Vandermonde right there with a big V. And what we're doing here is we're using this to get a formula that matches some data. So if you have some points and you suspect that that should fit some nice polynomial, then you might want to do interpolation to find a polynomial that best fits that, okay? But this exercise will show that it's not always great at fitting a sensible polynomial to the data. Sometimes least squares is, well, much better at doing it. So this will give us roughly, up to truncation errors, it'll give us an exact fit. Okay, now, I noticed straight away that this, okay, so first of all, I'll properly introduce this. So have a look at the matrix, okay, that I've displayed as a matrix here. So what I have is a 4x4 matrix, and it has x0, x0 squared, x0 cubed, and so on, right? So the entries are predictable in this Vandermonde matrix. And then we go down in the next row and we've got x1, x1 squared, and so on, right? So the rows increase in the subscript, the columns, the entries in the columns increase in the power, and that's an actual power, not another subscript or superscript. It's a power. All right, so this is multiplied by the coefficients of the polynomial that we're seeking. Okay, so if we have 4 data points, say P1, P2, P3, P4, and they have coordinates, well, actually, I should have said P0, P1, P2, P3, right? Because I've got subscripts 0 to 3. Okay, so if P0 is x0, comma y0, and so on, you get the pattern, right? Then basically I want to form this matrix, and where I put all the y values on the right-hand side, and then I want to solve the matrix system for the coefficients C0, C1, C2, C3, and those will be, you know, coefficients of the polynomial just like this. So this is Mathematica code here, incidentally, and this was suitable because this is a symbolic calculation, okay? So the coefficients are here, and I've used indexing to provide those, okay? So this is C0, C1, C2, C3 there, times these x to the power of something. Okay, so we should get a polynomial in the end as we solve that, right? So, but some of you may be familiar with the Lagrange polynomial. So I could see that if you did solve this, what you should get is this Lagrange formula, right? Now I got two hints. I got a hint from looking at the result and what the shape of the polynomial is. And it does a similar sort of thing to Lagrange interpolation in that you can fit rather exactly to some data, but it may not be a best fit in terms of something like least squares, right? So this is what the Lagrange formula looks like. Now you have a sum from 0 to n of the y parts of the data, and then you've got products, right? So I've separated two products there because I wanted to run this in the computer. But the way you write this formula symbolically is you just say avoid the case when I is equal to j, all right? And that looks prettier, but it's not. You want to be able to run this on a computer, right? Which I can do. So this is Lagrange. And it turns out that these two things are the same. So running this sum, this Lagrange sum, gives you the same result as solving this linear system here from the Waals Matrix interpolation. And that's not obvious until you do a symbolic calculation. So I've entered these symbolically, and then all of this here is me checking that this polynomial here that I get from Waals is the same as this sum formula that I get from Lagrange. So basically you see that I've entered this Mathematica there, LG equals this, and it's inside expand, so I've expanded, collected that, and then, so there's some superfluous calculations symbolically in here, but then I've expanded the difference, L minus V, so this one minus this polynomial, and then factored it, and then after all that, I could see that I get 0, so those are equal, right? But you get a hint here in that this relates to discriminants in number theory, okay? And being a number theorist, I have some familiarity with that. So the determinant of this relates to the discriminant. And that looked a lot like what we see in the denominator here. So I had a hunch that solving this system would give the Lagrange polynomial. And it turns out that it does, at least for degree 3, but I'm pretty confident that it should in higher degrees too. But I didn't get around to writing up a proof. Anyway. All right, so back to Julia. We want to be able to do this in Julia. Now keep in mind that Julia doesn't do symbolic calculations. Okay, so let's just have a look at the output here, right? So you get an idea. Now, okay, so we've got a few different colors here, right? So the big black things are data, all right? Some data points that you got from who knows where. And let's suppose that you wanted to find a fit. Now, obviously, the best thing to do here would be to fit this data using least squares because it seems to be a nice, well, it should have a nice linear fit, and that would be the most sensible thing to do because all of them are pretty close, well, to 0 relatively, okay? So a horizontal line seems to be a reasonable fit there. Whereas you can see this Lagrange polynomial, which is degree 5, well, that's a rather, it does fit perfectly, you see, right? But it's a rather silly thing to use as a predictor for what this data would be doing, okay? So that's the pitfall of using the Lagrange interpolation formula, in that you might be able to get an exact fit, but if whatever you're dealing with shouldn't be predicted by a degree 5 polynomial, then that would be a bad idea. But this makes a nice exercise here to do this computationally. Okay, so let's just have a browse at the code here, right? So what we're doing here, the first line would be to enter some x values. The second line, the y values, okay? So the x0, x1, x2, and so on. How many have we got here? It looks like we've got 6 of each, so 6 points. If you're thinking in terms of two tuples, you'd match the x coordinate and the y coordinate, and you'd have 6 points. Now let's scroll down. Yep, I see 6 points, so great. Okay, and then n would take the length of that. Well, you only need the length of one of them. Okay, now the next line is to form that Vandermonde matrix. Okay, so what you're doing is you're just taking the x values, you're doing indexing here. You've got an I plus 1 inside the bracket because we want to be able to start from 0 and go up to n minus 1. Okay, but when you're indexing, you don't want to say, I pull out the 0th entry of the vector, right? Because it's not, that's what Python would do, if I remember that right. I don't know about the latest version of Python. It's been a while since I used Python. But Python likes to start with 0, whereas some other software, Julia included, would like to start with 1 as the first one. Okay, so that's why we need an I plus 1 there. So this is just forming the Vandermonde matrix. Now the next line here is just solving that, and we can see C equals, but that's C a vector, right? Whose entries are the coefficients. And then we form a grid, -5 to 20. And then this would give us the polynomial that we're then plotting, okay? So that's the basic idea there. All right, now I think I need to enter some extra things here, and I can see we've only got 5 minutes to the end of the hour. I should probably rush out and get a drink of water before I do this again. But what I should do is draw your attention to the right Julia commands to get this to work. Okay, so I'll scroll down and see that. Well, it doesn't look like I wrote any down. Okay, so that suggests that it should work straight away. Let's try it. Or maybe I needed to get rid of pyplot to make that work. I'll try it anyway. Okay, that's going to take a while, but while we're waiting for that, let's go have a look at the next line. Okay, so P inverse. Now, I don't know what that syntax means, but if I speculate here, because I know that in the plot, we have a beta 0 and a beta 1. Now, I understand that that would be finding a least squares fit of the data, which would be a better fit than, or a more appropriate fit than the polynomial. Okay, so this one here is giving us a least squares solution to that. So beta 0 and beta 1 would be coefficients of a line of best fit, right? And in a line, you know, it's only got degree 1, so we should only have a beta 0 and a beta 1, where I would guess that the beta 1 is the slope. Okay, but there's a P, I, and V. Now, I'm only speculating because I happen to know what this calculation is about, but I speculate that this is a pseudo inverse, okay? Now, a pseudo inverse, you could think of it as a generalization of a matrix inverse. So it should give you the actual inverse if you have a square matrix that is invertible. Okay, but it works also to calculate a pseudo inverse of something like a 2 by 3 matrix. Now, what it also does is it allows you to do a least squares fit, okay? Because when you have the pseudo inverse times your y values, it's kind of like taking A inverse times the vector B, and you would get, you know, the answer to AX equals B. But well, in general, it gives you a best fit. So, and that is least squares. Okay, so I'm speculating that this is pseudo inverse PINV. Okay, so let's scroll up. I think this is run now, and so you can see it gave us the same thing as before. But let's try and run this and see if it goes through. I don't know that I did this one at home, but I'll run that with you and see if we get. Yep, it works perfectly. Okay, now the rest of this sheet, and I can see we're out of time and I want to run out and get a drink of water. The rest of this sheet deals with random matrices. It's a really nice exercise, so you should do that. But I'll just describe what's going on here. And actually, I could probably most efficiently do that with my PDF here. So I might just talk about Mathematica for a little bit. You can see the pretty nice Mathematica plots of the same. Okay, so in the next exercise, what we're doing basically is we're forming a random 3 by 3 matrix with entries belonging to the collection 1, 2, 3. Right, now here's some Mathematica code for doing that, where the 3 by 3 is in the second part. And then in the task, you're then building a function to do that. So this here is Mathematica code, but in Julia, this is the simple code for doing that, right? So we just build a function, rm round bracket with nothing in it, equals rand. Now that's a built-in function. And then the first input is 1, 2, 3. So this is a vector. So this is where we're drawing from. And then it's saying 3 by 3. So you can see that's the syntax to do that. Okay, and then the next part of it is to do 10 to the 5th of these such random matrices where you're drawing from 1, 2, 3. And then to form, well, to count how many of each one you've got, okay? So I'm describing Mathematica code here, but the Julia code is very similar, right? So basically, doing 10 to the 5th of these gives us a count of how many of each rank, okay? So now we've got 79,842 of rank 3. So that's 79,842 invertible matrices from that collection. Okay, now every time you do this, it should be slightly different. But if you look at the proportion, here I have 79%, or roughly 80% of those matrices are invertible when you do that. Okay, and how we measured that was that they had rank 3. Okay, so that's all, guys. So I'm about to repeat this. So I'll scroll back up to the top, but I'll rush out and get a drink of water from the taps. And I'll scroll to the top of this, and I'll see you in about 2 seconds for everyone coming in for this second session. For everyone at home, thank you very much for your help, and I'll see you next time. Okay, I'm back and hydrated now. So the downside is I'm 2 minutes late, but the upside is I don't have to spend 10 minutes or so setting up. So that's good. Okay, if you're coming in now, this is Math7502. And today we're talking about linear algebra with Julia. So what you should get from this is various ways and syntax for doing linear algebra things with the computer. So for example, how do you build a 3 by 3 matrix in Julia? And other things. How do you solve a system? How do you pull out specific elements from a matrix? How do you build random matrices? And how do you do some slightly more sophisticated things like interpolation and least squares? Okay. Now, unfortunately, I don't feel confident about my ability today to use the document camera together with this laptop. I'd like to spend a little bit of time to try it out, but I just didn't get the chance to do it today. So maybe another time I'll try that out. So I'll have to describe a lot of things verbally. Now, what I do have to help us out is a PDF that I made at home. Now, I made it with Mathematica because that's my native programming language. And while I'm sure I could be pretty good with Julia, but I'm not an expert on the syntax, right? Now I will say that having run through the problem set with Mathematica as well as in Julia, Julia's got some nice features in that it provides a simple syntax for a lot of matrix operations like indexing, pulling out specific elements. Whereas I found in some places Mathematica was a little bit awkward at that, or at least my implementation of it was a little bit awkward. And that may just be because I don't know the precise way to do some fancy indexing in Mathematica. Like what I see Yoni's done here in input 10 in Julia. And specifically by that I mean pulling out the first and the third column, for example, and that's even highlighted here. Okay, I see it's something in the chat. Diane Mezi says, can we get this PDF? Sure. So I think I'll just give this PDF to Yoni to upload to GitHub. So that should be fine. I think I'll have to ask him about that if that's okay, but that seems to be the most efficient way to do that. Okay. Oh no, right, I see that's an old comment. Is it? Is it an old one or a new one? You just said that now, Walla, did you? Yeah? Okay, I'm getting confused because I remember that somebody asked at the beginning of the first session about can you get the PDF too? And Wallace said yes. Okay, so I'm either having deja vu or yeah, this is it's saying 6:05. Great, good. So I think that's the present in Australia. All right. So where were we? So we've got to run this. Okay, if you're at home, you'll have and doing this now. For starters, you'll have to run using linear algebra. Okay, so how do we enter a 3x3 matrix in Julia? Well, you can see that the entries here in the same row are spaced out by a space. And then to make a new row, we put a semicolon. Okay, and you can see straight away underneath the output. So I'll run this again. And it'll take a little while, but there it is. 1, 2, 3, 4, 1, 6, 7, 8, 1. Great. Now the trace. You want to know how to take the trace of a matrix. Okay, what is the trace? It is simply the sum of the diagonal elements of the matrix. Okay, so 1 plus 1 plus 1 is 3. So that's great. Good. Okay, now also you want to know, how do I take the determinant of a matrix? Well, you can just write in DET, round bracket, A, and in this case we have 104. That looks about right. So I trust Julia on this one. All right, but next we see in line 10, or in 10, another formula for the determinant of a 3x3 matrix. Okay, so what we're doing basically is going across the first row and doing some indexing. So the A11 entry, so first row, first column, we have the number 1. But we pull that out by indexing, which is very important to be able to do. And in fact, you want to be pretty good at this. And learn all of the fancy ways to pull out specific elements, because they certainly come in handy. Okay, so we pull that out with the square bracket, A, then square bracket 1, comma 1, and then multiply with an asterisk. So this is doing a scalar multiplication here, but the same asterisk will do a matrix multiplication as I've seen below. Okay, now we're taking the determinant of the 2x2 matrix that we obtain by crossing out the first row and the first column. All right, so in other words, 1, 6, 8, 1. We take the determinant of that one and multiply it by the 1 in the top left corner, and that's the first thing that we're adding together to get the determinant if we were calculating this by hand. Okay, so you can see that this is going to agree because we got 104 below it. Okay, but this is really, you can think of it as an exercise in indexing. All right, now how do we do this? So what we're doing here, you see 2:3 and then a comma, 2:3. So what we're extracting is rows 2 through 3 and columns 2 through 3. And then we're taking the determinant of that matrix that we formed. Okay, now next we subtract the next element in the top row, which is 2. So we subtract 2 and we pull that out using a square bracket 1, 2. And then we multiply by another determinant. And that determinant would be the determinant of the matrix obtained by crossing out the top row and crossing out the column that that 2 is in. Okay, in other words, the middle column, we would cross that out, and what we would have remaining is a 2 by 2 matrix 4, 6, 7, 1. But we want to take the determinant of that in our determinant calculation. So now you can see there's slightly different syntax in this compared to the other 2 determinants in this formula. But that's great because it gives you an opportunity to do something new. And that is to take out, so the first thing is take rows 2 through 3, all right? And then from that, specifically extract columns 1 and columns 3 and form a matrix out of that, okay? And then finally take the determinant and use all of this in our formula. Okay, and the last one is nothing surprising. It looks a lot like the first. So we have the third entry of the first column, that 3, and then we want to multiply by the determinant of the matrix 4, 1, 7, 8. But to get that, we take rows 2 through 3, and then columns 1 through 2, okay? So that's somewhat different to what we see in the second entry there. All right, and so we better run this. 104, yep, good. Okay, we'll run this one, and we got 104. So those agree, that's great. All right, next, compute the determinant using the first column. Well, that's an exercise. Let's not do that because in the last session I pretty much ran out of time. But I was likely a chatterbox in the beginning on too many simple things. Okay, now I'm going to pull up my PDF here and discuss this because I can display some symbolic matrices here rather easily. Okay, but I'll go down and show you something. So the matrix that was entered, and it was, I believe, yeah, that 3 by 3 matrix there. Okay, so this is Mathematica here. I've taken the inverse of A, displayed it as a matrix. Below that, I've taken the numerical version of the same and displayed that as a matrix. But what I want to point out is that in Mathematica here, I am displaying the rational numbers in the entries, all right, because the actual exact inverse has rational numbers in the entries, where you see in the denominator is 104, which was the determinant of our 3 by 3 matrix. So that's an exact inverse, but what Julia is getting is an inverse of the truncated version. So it has truncation errors in it, right? Nevertheless, A times A inverse is going to be fairly precise. So let's have a look here in Julia. So we'll do this. So here we're entering the inverse, just using the INV command. Okay, and that takes a little bit of time, even though I've run it once before. And we see some decimal numbers. Okay, so we get 6 decimal places after the decimal place. But those are approximations of these rational numbers, and they're cut off, right? Because now, yeah, so if I actually calculated what is the exact value of minus 47 divided by 104, well, that would be a repeating decimal expansion, right? Because it's rational. So you definitely know that these are chopped off, truncated. Okay, now, nevertheless, we can take the inverse of this inverse, and we'll see straight away that it wasn't so bad. So the original one had integers in it, but the inverse of the inverse is supposed to be the same. What we have is decimal numbers of the same. So it's just changed the number type because it introduced decimal numbers in the calculation of the inverse. But you can see that that result is pretty good. Okay, let's have a look down here. Okay, in the next problem, we're going to look at this matrix equation. And so what we want to do is solve for x. X is a vector, lowercase b is a vector. These have these exact values. C is 1, 2, 3, 4, excuse me, and so on. So I'll put that in memory now, and that ran quickly. Okay, but we want to do some symbolic calculations before we try to solve this, okay, because that will make our job a lot easier. Okay, because Julia is not going to be able to do the symbolic rearrangements that we might do by hand or in other software. So let's think about how we would simplify this by hand. And after all, this is quite a lot of this course is linear algebra, so it's best to learn a few tricks of linear algebra to make your life easier. All right, so we want to solve Cx plus the transpose of x transpose times d equals x plus b. So on the right, we have a sum of two vectors, and on the left, we have products between matrices and vectors. All right, now let's talk about the transpose of the product of A times B is equal to B transpose times A transpose. So that's an identity that we need to use here. So applying that rule, we can view X transpose D all transposed as D transpose times X. Okay, so that would be our first step in simplifying this. Next, what we would want to do is collect all the X's on the left-hand side, because you can see we now have a hope of doing that, given that the second term is D transpose times X. Okay, so we subtract X from both sides, but we can view the minus X as minus identity matrix times X. And that's convenient because it permits us to factorize out the vector X from each of the three summands. So we can factor that out on the right. And so that is our third step here, or second step, I suppose. So what we have remaining inside the bracket is C plus the transpose of D minus the identity matrix, and that is all times X, and that is equal to B. Okay, so that now is in a form that we could solve more easily, because we could now declare A is equal to C plus D transpose minus I. Okay, and the syntax for transposing is just this dash. Put this in memory now. And you see that Julia knows that uppercase I is the 2 by 2 identity matrix rather than say a 3 by 3 identity matrix. So I speculate that it gets that through context, because you can't add a 2 by 2 matrix to a 3 by 3 matrix. So that should be fairly, at least for a human, right? So I guess you could say it's impressive that Julia knows that that's a 2 by 2 matrix. All right, so we've put that in memory. All right, are there any questions out in the audience? No? Okay, good. Let me have a peek at the chat. Nothing new in the chat, okay. All right, so now that we've entered the matrix A into memory, we can then just use the solve mechanism here in Julia to solve AX equals B. All right, so we've got X solution, or X sol equals A backslash B. Now that's a lot like what you would write in MATLAB if you know how to use MATLAB. To do something similar in Mathematica, I would write linear solve and then A comma B. All right, so let's run this. And we get two decimal numbers in an array, 0.25 and 0.3125. Okay, that looks good. Now let's check that this satisfies the original equation. All right, so we just take, this is the left-hand side of our original equation. So let's run that left-hand side. We get 1.25 and 2.3125, good. Now the right-hand side, x solution plus b, because remember we've calculated x, but we've called it x solution or x sol. So we want to add that to b. And great, we see that those two are the same. All right, now next, we've got some mysterious syntax that does something, well, we can guess on the third line, right? What this is meant to do. So we're taking a dot product of two vectors, and then we're taking the dot product using a matrix product in the second line. Okay, but you might consider these two that were entered to be somewhat mysterious. So let's have a look at my PDF notes on what those are meant to be. So scroll down and find that. Okay, so now that says build a 5x1 matrix U of ones. Okay, and then that's Mathematica code for doing that, constant array, where I say what I want the constant to be, in this case 1, and then I give the dimensions, okay? Now in Julia, the corresponding thing is fill. In other words, I'm filling my vector with ones, so that's the first entry there, and then the second one is 5, to mean that I want 5 of those in a vector. Okay, so that's 5 ones in a vector U. And the natural syntax for a vector the natural output for a vector in Julia is a column vector, whereas vectors, of course, could be rows or columns, right? But in Julia, the output is columns, and Yoni will tend to write things to be assumed as column vectors in his lectures, I would guess, because he does so in the assignments. Okay, now the next one, in Mathematica, I would write table. Now I put an extra bracket around that, right? Because I don't just want a list of the numbers 1 to 5, because I want this to agree. I want it to be a column vector. So in Mathematica, I need to put an extra bracket around that to make this a column vector. All right, so yeah, so it's just the list of numbers 1 to 5, but in a column vector. So in Julia, it looks like 1:5, and that just gives those as a column vector. But then the last entry here is dot u comma v, and then we see comma u dash for u transpose, and then that's times v. Okay, so as you know, there are two ways to calculate a dot product. In the first way, well, the dot product of two vectors is just you take the product of each of the corresponding entries in each one and add them all together, right? So you multiply across and add the results. But it's convenient to be able to do this with a matrix product for the sake of, doing some theoretical calculations in linear algebra, or to do this with a computer like in Julia. So yeah, it would just be u dash v. Now, one thing to note is that we haven't included a round bracket in the syntax in Julia. So let's go back over to the notebook and we'll run this. Okay, and we get round bracket 15, 15. So we have a 2 tuple there, but we didn't put any round bracket in here. So just to experiment, what happens if I include a round bracket here? Let's see what happens and see if we get anything different. Okay, no, we still get the same thing. So that appears to be optional there. Okay, optional, great. All right, now in the next one, I'm just going to put a semicolon there. Does that comment out? Okay, great, it does. That was just a guess, incidentally. Right, so the next one, now we see some commands, right? And you get a hint of what this is meant to do, but let's have a look at what the question would say. All right, because you may not know what reshape means or collect means in Julia. Okay, so I'll go over to my PDF here. So the instructions would say, form a list of the integers from 1 to 21, and then form a 3x7 matrix in which we count from top to bottom. All right, so I did this in Mathematica, and because Mathematica likes to think in terms of rows rather than naturally in terms of columns, so I would have to transpose that to achieve the desired effect here. All right, in Mathematica, that is. All right, but perhaps in Julia it's more natural in columns, so that's the way it comes out from top to bottom in the counting. Okay, so the first step is to form a list 1 to 21, and that you can actually just do with collect. So I'll uncomment that again so you can see it. You've already seen it, of course, but hang on, what do I? Okay, I'll try that again. Running. Okay, so you see there's a column vector containing 1 to 21. Now reshape is just saying take that and make a 3x7 matrix out of those in a specific way by breaking it up into triples, I guess. Yeah, because in Mathematica I would just put partition, right, which would break the result up into triples. Or I think I actually put partition 7 maybe because it likes to think in rows. No, I broke it up into triples and then transposed it. Okay, right. So reshape does this in a somewhat different way, I guess. So in other words, give us a 3x7 matrix out of it. All right, so we need to put this in memory. So let's go ahead and do that, because next we need to talk about the matrix A and its rank. But you might be wondering now, what is the rank of a matrix? Okay, so the rank of a matrix. So first of all, let's talk about the row space of a matrix. Now, the row space of a matrix is a vector space spanned by vectors, okay? But those vectors are the vectors consisting of the rows of the matrix. But what you might want is a great convenient basis for your vector space, which is the row space. And so one way to get a very nice basis is to row reduce, or take the row reduce echelon form of your matrix, okay? And so you end up with some pivots. I'll just run this calculation, okay? So rank, we get 2, but I haven't explained that yet. Now, I seem to recall that this was missing in the Julia file that Yoni provided, okay? And incidentally, I'll just tell you how to get that. So given that you're in Math7502, I presume, you have access to the Blackboard site. You go through the Blackboard site to the course webpage, scroll down to the GitHub link, select the GitHub link, then you find the folder called weeks. You find this file in the folder called weeks, but it this time does not have a download button like the last time had for the first prac session. So what you have to do is look for the button that says raw, R-A-W. You right click on that button and you save as, and then you can save that on your own system and run all of this stuff, okay? But it was missing the commands. Now, if I remember right, I needed to do this one first. So I'm going to copy and paste this and delete it. So it goes in the right spot. Control C, and then I'll delete it. And then I'll just press Shift Enter. Okay, so this is the first one we need. Import pkg, semicolon, pkg.add, and then we put in quotations row echelon with a capital R and a capital E. Okay, now that's running, but underneath there you can see the row reduced echelon form of the matrix A. Okay, I'll click here, but now I'm hoping by pressing insert cell above that I can get a cell above, because what I need next is what I've copied. I'm going to paste that. So I paste that next, but this is still running. I need to wait for this. It takes a little while. Guess maybe that's one of the downsides of free software. But there are hopefully a lot of upsides too. Okay, that seems to have gone through. All right, now let's run the next one using row echelon. Okay, that goes through straight away, I guess. And now we can use the row reduce echelon form function. And great, it's row reduced that. So we have Gauss-Jordan reduced form of the matrix A. And so these, so let's have a look at the first row. Okay, we've got a pivot there, the number 1, it's got zeros below it. Then we've got another pivot 1, it has zeros to the left of it, zeros below it, and zeros above it. Okay, so these two are pivots, and then the vectors consisting of the rows, that forms a basis for the row space. So these two, there are 2 of them, so we know this vector space has dimension 2, and it's spanned by these two rows. Okay. All right. So yeah, and because there are 2 of them, the dimension of this is 2. But there's a nice result in linear algebra that says the row space of a matrix is equal to the column space of a matrix. And so in terms of columns, the dimension of the column space is 2. And I'm trying to select the columns, but that doesn't work. But I'll just point it out with the mouse. So we've got column 1 and column 2. That is a basis of the vector space consisting of the columns in this matrix. So in other words, every column in this matrix is a linear combination of the first 2 columns, okay? So in other words, -1, 2, 0 is a linear combination of the first 2 column vectors in this matrix. And in fact, you can see clearly that it's -1 times the first column plus 2 times the second column. Okay, now we want to be able to do this with Julia, right? Computationally. So, and this gives us another opportunity to use indexing. So here we see x3 equals a square bracket, and then we have a colon there, right? So that colon refers to taking all of the elements in the column, I guess, right? I find this difficult to say. Anyway, so, but we're taking columns 1 through 2. So all of the entries in columns 1 through 2. Okay, and form a matrix out of that. Now that's going to be a 3 by 2 matrix, right? Because we've got, well, I can't do that. Okay, so 3 rows, 2 columns. That's what we take out of this. And then here we have all of the entries in the 3rd column, okay? And that is a vector, right? So here we're solving an equation, ax equals b, using the backslash, which is a lot like what MATLAB does. All right, so let's run that, and that gives us the answer, which is that the answer to the equation ax equals b, where this part of it is our matrix A, and then the 3rd column is our vector B. All right, so we get an answer -1, 2. So these are the coefficients that we need to multiply each of the first 2 columns by in order to obtain the 3rd one. So this is showing you that that the 3rd column is in fact a linear combination of the first 2 columns. Okay, now down below we have a whole bunch of similar calculations showing that the other columns are linear combinations of the first 2 columns also. I'll skip that. Okay, now here we're, okay, rank is 2. Now I don't know whether I said earlier, but the dimension of the row space equals the dimension of the column space, and we call this the rank of the matrix, okay? So that's unambiguous, right? Because those 2 things are equal. All right, next we have some other syntax in Julia. So the next command says, take a vector containing ones, but 3 rows and 1 column, and then multiply all that by -1. So what we have is that the vector v is -1, -1, -1. So I'll put that in memory. Okay, next, calculate the norm. All right, so this is just the Euclidean norm, as in the one in Pythagoras' theorem. So this is the square root of the sum of the squares. So that would be the square root of 1 squared plus 2 squared plus, sorry, 1 squared plus 1 squared plus 1 squared, which is, this is the square root of 3, right? So what we're doing here is comparing these two. So SQRT3. All right, then what I did in the previous session is I wrote \SQRT3. And then press tab, because I was hoping that would give me a nice pretty square root symbol over the 3, like I would get in Mathematica if I did something similar, although I would do that with an uppercase S and a square bracket. Okay, but this didn't work, right? So it doesn't give me a nice pretty square root of 3. But nevertheless, the LaTeX command for pi does work. Okay, so whoops, I press Shift and Enter. Okay, whereas I'm supposed to press Tab. Okay, and now that gives me 3.14159, blah, blah, blah. Another number that I thought was a good idea to memorize when I was a kid. No, I don't think that was such a great idea. Okay, anyway, norm v comma 1. So what this is the L1 norm. So that is just the sum of the absolute values of the entries of the vector, okay? So in other words, since we have -1s in our entries, this would be +1, +1, +1, we get 3. Okay, great. Now there's an infinite norm too. So that is the maximum absolute value of the entries. Okay, so not surprisingly, we get 1 for that. And in this next cell, we can double check that with a vector that we enter ourselves, 1, 2, -8, 3. Take the infinite norm of that, and we get 8, so being the maximum absolute value. Okay, next important function is normalize. So normalize, so what we're normalizing is a vector consisting of 3 ones. Okay, but normalize means take the unit vector obtained by dividing by its norm. All right, so in other words, divide each of the entries by √3. Okay, so we get 0.577. Okay, norm v is 1. Okay, next, now I didn't get this one to work straight away on my own system, and I didn't get it to work on this laptop, okay, but maybe I got it to work at home. And since we're a bit short on time, I'm going to skip this one, although you at home should probably give it a go because you get a nice pretty picture with a red ring around some data, and you can see Yoni's gone to a bit of trouble to make that work. So it's a bit of a shame to skip this. All right, so yeah, anyways, but we'll skip it. I want to have a look at the next one. All right. Now the next one, I'll just go to the picture first, okay? So the picture, what we have here is a pretty picture containing some data. These are black points, 6 of them. Okay, and this is a problem on fitting the data using 2 different methods. Now, the method that, well, the blue curve that passes through there, it's a polynomial that passes through there, so that's a function. So you could fit this data to a polynomial, right? And in this case, since we have 6 of those, 6 minus 1 is 5. So we could fit that to a polynomial of degree 5. Okay, but now if this data were about something like, I'm just trying to be creative here, but the height of six, well, I want to say twins, but that's not the right word, right? What happens when someone gives birth to 6 people at the same time? Is it called sextuples? Maybe, all right? But if you had 6 children that came out of the womb at the same time, they might have similar heights, okay? So you wouldn't want to predict their heights using a degree 5 polynomial, because that would just be silly, right? A better way to do that would be to use a least squares linear fit, because you would expect that there would be just some little errors or discrepancies, maybe due to nutrition or something, right? Nevertheless, sometimes it's convenient to fit data to a polynomial, right? Maybe that data naturally does fit some particular polynomial, like a quadratic polynomial. And so in that case, you would want to take a polynomial fit, right? Now, the method that we're looking at here is involving a Vandermonde matrix, okay? So I'm going to show you that first, but some of you may be familiar with Lagrange interpolation formula, and those are actually the same thing here. But let's have a look. And you don't fully get the idea that those are the same until you do a symbolic calculation, but Julia doesn't do symbolic calculations, so sometimes it's handy to be able to do a symbolic calculation in other software, okay? So don't go and delete your Mathematica just yet. All right, so I'll scroll down to where I've displayed that matrix symbolically. Now here I've made it smaller just to make it more convenient, okay? So what I have here is I've displayed a 4x4 Vandermonde matrix here, round about where my mouse is. And so what I wanted to do is input that symbolically and compare it with the Lagrange interpolation formula, all right? So this is probably a little bit bigger down below. Now, it involves a sum and a product, okay? But here you see 2 products. Those are just 2 products multiplying together, and I put that in myself, whereas normally you see this formula in terms of, it would say down at the bottom with a single product that I is not to be equal to J. Right? But if you're putting this together in a computer, you just want to skip that, right? So it can't be as pretty as you would write it out by hand. Anyway, so this is the Lagrange interpolation formula. Now, so the x's that you see here are the x coordinates of your data. So suppose you had 4 points. The y's that you see are the y coordinates of your data, again, 4 points. And you're seeking coefficients of a polynomial. Well, you're really seeking the polynomial, but you obtain it through the coefficients, finding the coefficients. And so you might call those C0, C1, C2, C3 if this is degree 3. Okay, so yeah, so one way to do this is to solve the matrix equation, where we have the Vandermonde matrix here. Now, presumably, when you enter this, the x0s, the x1, and so on, and the y's, they would be numbers, just numbers that you got from your data, right? Whereas you're seeking to find the coefficient c. Okay, but I have entered this in Mathematica entirely symbolically because I wanted a symbolic output to compare symbolically to the Lagrange formula for interpolation. Now, the way I compared those in this case is so what I have here is V is just the sum of the coefficients that I got out of solving that and putting that into memory times the x to the power of something. Okay, and add those together, and I should get a symbolic polynomial, right? Whereas all of the coefficients c, they are in terms of the x's and the y, and they're rather nasty. They're enormous in size. So you wouldn't want to do that by hand there. But it's nice to do with a computer, okay? Symbolically. And now I do the same well, I do the calculation using the Lagrange formula, put that in memory, and then I take the difference between the two of these, all right? The difference between the two polynomials. And I find, after expanding and then factoring it, that I get a 0. I get 0. That says that the two are the same. Okay, now that most likely generalizes, and you get a hint to this fact because this van der Waals matrix is related to discriminants of polynomials, and those are important in number theory, right? And they have a nice formula that looks a lot like what you see here in the denominator, a product of differences. In some cases, these would be of various algebraic numbers. But that gives you a hint because this is related to the determinant of this van der Waals matrix is related to the discriminant, and this is appearing in the denominator. And if you actually solve this, you would have a matrix inverse, right? And where the determinant is in the denominator of the entries. Okay, so that kind of gives you a hint that this is the case. Anyway, let's go back to Julia and talk about how you form the matrix and then how you solve that. Okay, so in Julia here, you've got all the x values, all right? You've got all the y values, and if you paired those together, you would have, for example, the point -2, 7. All right, and so on. So you take the length, well, this is going to be 6. Next, what we're doing here is we are entering the van der Waals matrix, okay? So we're just forming a matrix, and it consists of the x values. We're indexing, but you see an I plus 1. And that's because in Julia, rather than like in Python, where you would start with a 0 as the first element, in Julia, 1 talks about the first element of a vector. So we need to add 1 because we want to start our i's with 0, so that the first power is 0. Okay, and so that we get something like what you see over here. But I guess this is 6 by 6 or so. Okay, and then this here, f1, that's the polynomial, but remember, this is not symbolic. What you're actually getting is a function. You're building a function here. Okay, and then you're going to plot the function down below. So that's how this works in Julia. And then you get some nice commands for how to do all the colors and so on, and the labels. So that's convenient. I mean, you probably want to keep this somewhere so that you can use that in your own stuff later and change things, right? Because, you know, that's a lot of writing. You'd have to go and look that up. Okay, so if I run this, let's see if we can do that. Okay, that ran rather quickly. Good. And you can see it fits. Now the red one is a least squares fit, right? And so because that's a line, and in this case, it's a line in the plane, so that would be described by, say, you know, the line y equals mx plus c, but in this case, we'll use a beta 0 for the c and beta 1 for the m, I suppose. Okay, now I don't know enough about the Julia syntax to precisely know what this is, but I speculate that P I and V, because I happen to know that this is you can clearly see this is a least squares fit, right? And I happen to know that the pseudo inverse is used in least squares, or it could be used in least squares. You don't have to use it, but it makes a convenient way to do a least squares fit using linear algebra. So this seems to be built into Julia, that you can calculate a pseudo inverse. Now, you could think of a pseudo inverse as a generalization of the inverse of a matrix. Okay, because if you have an n by n matrix, in other words, a square matrix, and suppose that that square matrix has a non-zero determinant, then it should have an inverse, right? Okay. But now suppose that you have something like a 2 by 3 matrix, but you still want a matrix that acts in some ways like an inverse. Okay, we know that the inverse of a 2 by 3 matrix does not exist, but you can form a pseudo inverse anyway. And what that does is when you solve AX equals B using the pseudo inverse, multiplying the pseudo inverse on the left on both sides, what you get instead is a line of best fit, okay, which is rather convenient because it allows you to do least squares. Okay, so I'm speculating that PI and V means pseudo inverse, P for pseudo. All right, so let's try this out, and it works straight away. So great, okay, good. All right, next problem. So it's 10 to the hour. So if you need to go on to your next class, go for it. But I'll briefly talk about this next problem without fully doing it. So the next one builds a function consisting of 3 by 3. So this 3, 3 for 3 by 3, consisting of 3 by 3, a 3 by 3 matrix with 1, 2, 3 in it. So randomly 1, 2, 3. I'll scroll into my PDF, see if I can find an example displayed as a matrix. There you see the pretty polynomial. All right, looks like I've gone a little too far. There we go. So here's an example. So here's a 3 by 3 matrix consisting of randomly chosen integers in the collection 1, 2, 3. Okay, and then some Mathematica code above that for doing the same. All right, but back to Julia. So that's what this does. You're building a function to do that. And so in Mathematica, you can see I also built a function to do that. Okay, good. So let's put that into memory. Sure, good. Now let's try it. Okay, great. And we'll try it again. Okay, now this time it's different. Good. That's what we expect. Okay, and the next one. Now I reckon there are probably some things to put in beforehand. All right, but let's have a look here. Okay, so next what we're going to do is construct a list of 10 to the power of 5 such random matrices. Okay, and we'll call that list maths. And then what we're going to do is take the rank, I believe. Yeah, I thought we were taking the rank of these from memory. I don't see it. My eyes are going a little bit strange because I've been staring at the screen for a long time today. But good thing we're almost done. All right, so what we're doing is basically taking the rank of each one, and then we are counting how many matrices did we get that were of rank 1? How many did we get that were of rank 2? How many did we get of rank 3? And so we count those, and what we want to know is what is the proportion, right? All right, so it turns out that when you do this, so when I ran this, what you're seeing here is I got 79,842. But what you really want to know is the proportion, because that proportion is probably going to stay roughly the same. So in other words, how many of these had rank 3? And if they have rank 3, then they are invertible. So how many of these random matrices were invertible? Okay, and it turns out in this case, roughly 80% were invertible. So let's go back to Julia. Okay, in Julia, it looks like we got a very similar number, off by, say, 22 or so. And then Julia is counting, it's counting how many were of each rank. And so we can see we get very similar numbers. Now the last command is, let's see, I believe that is the sum of the first 3. So maybe. And so it doesn't add up in this case because I've run this on different occasions, right? And each time they have different random matrices in it. So let's see if this runs now. Okay, and it looks like I need to include a package, but you see exactly what to include right here. So highlighted here is what you need to put in order to get this to work. So I won't do it, but and in fact, I think I'll just knock off here. So thanks everyone. I'm going to close that. My lips are a little dry. I think I need another drink of water. Seems like I've given a 2-hour lecture rather than a tutorial, but anyway, that's life. So I'll close this, and thanks very much for participating. And now I see there are a lot of things in the chat, so I'll try to answer some of these questions. Okay, so Jonathan, you say, shouldn't we just divide by, let's see, how many zeros have you got there? Yeah, you divide by that, and that's how you get that proportion. But you can divide with your count, right? Because you've got that originally, so 10 to the 5th. And that's how you get the 0.79842. So yeah. All right. Yes, you can put array 1:5 to see the output. Yeah, 1:5 is an array, so that should be the numbers 1 through 5. Okay, but let me have a look at your question. So V is a row vector, yes. No, it's a column vector. I get the impression, because I haven't spent a lot of time using Julia, but I get the impression that they seem to all come out as columns. Am I right, Walla? Yeah, so Walla says yes, they all come out as columns. Whereas, at least in Mathematica, you can make things a row or you can make things a column. They just have a slightly different syntax in the input and the output. Okay, so let me scroll up and see things you've said earlier. So looks like Walla has kindly answered those questions that I missed. Okay. All right, guys, that's all for now. So thank you. I'll see you next time. Maybe by then I'll get the doc cam working, and hopefully we can record that. I might have to ask Yoni to set up recording through the system, through the UQ system, but we'll see. All right, good night, everyone. Hope you have a great week. Okay, thanks. So close that, stop sharing, and I'll end the session.